Hello everyone, I'm Jayadev Naram and I will be presenting the paper Non-Negative Low-Rank Tensor Completion via Dual Formulation. This work was done by me and Tanmay K Sinha under the guidance of Professor Pawan Kumar at IIIT Hyderabad. In recent years, tensor-based methods have become a common alternative to the matrix-based methods when dealing with multidimensional data. A common problem in this setting is the problem of tensor completion, where we are given a partially observed tensor y and want to recover the original tensor. We assume that the underlying tensor has a low rank, and a typical way of formulating this is given in equation 1. The first term in the objective is the least square loss over the indices omega for which we know the value, and the second term is the low rank promoting regularizer R. In many applications of tensor completion, such as image recovery and video completion, the underlying data is non-negative. However, the above formulation does not take this into account, so we explicitly enforce non-negative constraints as shown in equation 2. Now we present our formulation. We want to learn W as a sum of k tensors, where k denotes the order of the tensor. We use the trace norm regularizer as R, which is introduced in an earlier work. In equation 3, note that W subscript k indicates the mode k unfolding of the tensor W. Following this, we use the results from the duality theory to construct an equivalent minimax problem. In the minimax problem, we have the dual variables theta k, z, and s. The primal and the dual solutions are related as given in equation 5, where we make use of k-mode product between a tensor and a matrix. Note that k-mode unfolding of the kth component of the sum will have rank which is determined by theta k. We impose a fixed rank constraint on theta k by writing theta k as UK transpose, where theta k belongs to spectrahedron manifold. Then the minimax problem reduces to the following form. The spectrahedron manifold is a Riemannian manifold, and the outer optimization problem is an optimization problem on Riemannian manifold. This can be solved efficiently using the techniques from Riemannian optimization. The inner optimization problem can be seen to be convex over Z and S, so they can be solved efficiently using conjugate gradient and projected variant of conjugate gradient respectively. We have tested our algorithm over various datasets of color images, hyperspectral images, and videos. In this table, we present the RMSE scores of the proposed method compared with several baseline algorithms. We have considered 10% to be the training data. The proposed method achieves the best or the second best scores over all datasets. Next, we show a slice of the original dataset and the reconstructed tensors by various methods for the same data fraction. In the color image datasets, LRTC-TV performs better than our method. We suspect this is due to the local smoothness property that is preserved by LRTC-TV, which we do not take into account. But in the other datasets, which seem to lack the local smoothness property, LRTC-TV gives a bad reconstruction. Lastly, we show a visualization of the component tensors. Here, slices of the original tensors is shown along with the reconstructed tensors and its component tensors. We see that the ith component tensor learns the original tensor in the ith mode. This concludes the presentation, and thank you.